Thank you, Arslan. And also thank you to all the organizers and all the participants here. I hope you saved some part of your energy for the last talk of the day. I know it's a very hard day, it's a very difficult day for every one of us. This summer, we studied with Serhat on differential geometry. And we tried to find some interesting topics, because I always try to do that. And we decided to study a specific theorem. It's a very basic theorem. I don't want to spoil it right now. You see it on the outline, but okay. Serhat is a senior student in Boğaziçi University in the mathematics department. And he will give you his talk now.
Special thanks to August. He was very helpful. And he was very helpful. Thanks to August. I am Serhat. Hello, everyone. I am from Boğaziçi University. Today, I will going to talk about a theorem, which name is theorema egregium, and I will talk about its applications. Theorem is mainly about mapping a surface to a surface and shapes of surfaces. So we will definitely look surfaces. What are they and how they bend in a space. To understand clearly the surface, we will begin with some basic concepts, curves. And as I mentioned, theorem is about mappings. We need to introduce also isometries. So let's begin with the curves. What is a curve? A curve is a differentiable function from an open interval I in R to R3. Here's a graph of an image of a curve, and you can see a vector here. It is tangent vector. If we take a derivative of the vector, then it gives us a vector which name is tangent vector, and the other name is velocity vector. And if we take length of this vector, we call it as a speed. So we will find the turning of the curve, bending of the curve. To do that, we will examine the change in the direction of the tangent vector. So we will take derivative of the tangent vector. So in order to do that, everywhere on the curve, tangent vector should exist. So we don't want sharp points in our curve. We want a nice curve. What is a nice curve in mathematics? It's a regular curve. Regular curve is a differentiable curve such that its derivative never vanishes. Its derivative never equals to 0. And then, as I mentioned, we will look at the turning, but the derivative, the changing in tangent vector depends on two things. One is the change in the length of the tangent vector. The other one, change in the direction of that vector. So to explain the turning, we should only focus on the direction of the vector. So we want to fix its length. There is a theorem. If we have a regular curve in our hand, then we can reparameterize the curve such that it has a unit speed everywhere on the curve. The length of the tangent vector is 1. So now we can examine the bending of a curve. If we take derivative of the tangent vector, as I mentioned, it's only depend on the direction. So it will give us a numerical measurement of the turning. If we take the length, it will give us a numerical value. And the length of norm of the T prime, we call it is a curvature. Curvature is simply how much the curve is bending. So we introduced an important concept. As I mentioned, we need other other notion, which is isometries, to explain our theorem. What is an isometry? Isometry is a mapping that preserves length. In mathematically, for every P and Q in R3, the distance between P and Q equals the image of distance between image of P and Q under there. If this property satisfies, then this function is an isometry. So isometries are length preserving functions. So after the definition, we can look at the fundamental examples of isometries. The fundamental examples of isometries are translations, reflections, and rotations. These are fundamental. You see the picture. In the picture, there is a pentagon. If you move a pentagon from a point to a point, the lengths of the edges will stay the same. So the lengths are preserved. The lengths don't change. Didn't change. So you can apply the same logic the other two. So these are the fundamental examples of isometries. So we introduced two important concepts. However, the theorem is about mainly surfaces. So we should define the surfaces. What is a surface? But to define a surface, I need a tool. The tool is a coordinate patch. Coordinate patch is a one-to-one regular mapping from D of R2, is an open subset of R2 into R3. So you see the domain of the function and you see the image of the function. This is the coordinate patch. Now we can define a surface. Surface is a subset of R3. Let's call this subset M. And if M satisfies a property, we call it as it is a surface. What is this property? For every point in, for every P in M, if there exists a patch such that whose image contains a neighborhood of P, if this property satisfies for all point in M, we can call M is a surface. We can say that M is a surface. So broadly, roughly, you can think D as a rectangular paper. And if you can cover this shape with these papers, then it is a surface. So simply surface is that. But we want to examine the bending of a surface. So as in the curve, we took the derivative of the tangent vector. So we need to take derivative on a surface, but we don't know how to take derivative on a surface. So we need other tool. The tool is covariant derivative. Let W be our vector field and V be our tangent vector at the point P. The covariant derivative of our vector field along the vector with respect to V is this. And the geometric meaning of this, initial rate of change of the vector field when we go along that vector. So the geometric meaning is this. Now we define the derivative. Now we can take the derivative of take the derivative on a surface. But in a curve, we take the derivative of a tangent vector. How can we generalize to a surface? We can look at the tangent vector, tangent plane. The change in the tangent plane will give us a bending of a surface. So the tangent plane can be defined by its unit normal vector fields. So U is a unit normal vector field. The covariant derivative of U with respect to V, dot product V, is our normal curvature. It gives us a bending of a surface, simply. Why we call normal? Because we use normal normal vectors. So the change in the u is also will give us a change in the tangent plane. So here is an important thing. The normal curvatures depend on the vector. So there are infinitely many choices of V. So there are infinitely many curvatures, normal curvatures. These all don't give us a valuable information. So we can choose some specific ones, which are minimum of a normal curvature and maximum of a normal curvature. These are principal curvatures. Maximum of a normal curvature, let's denote it K1. Minimum of a normal curvature, let's denote it K2. After we after the definition of this, we can define other curvatures by using K1 and K2. The curvatures are the Gaussian curvature and the mean curvature. The Gaussian curvature is multiplication of K1 and K2. And the mean curvature is K1 plus K2 divided by 2, arithmetic mean of K1 and K2. And they both have a geometric meaning. And to better understanding, we will look at the geometric meaning of Gaussian curvature. And the geometric meaning of the Gaussian curvature depends on its sign. So if the Gaussian curvature is positive, then K1 and K2 both have the same sign. They all can be negative or they all can be positive. And since these are minimums and maximums, minimum and maximum, all values between them have all the same sign also. So the surface will move away from its tangent vector in all directions, and it looks like this. It's a spherical shape. If the Gaussian curvature is positive, the surface is a spherical shaped surface. If the Gaussian curvature is negative, K1 and K2 have the different signs. One is positive, one is negative. And this means that in one direction, surface will bend upward. In one direction, surface will bend downward. So it looks like this, and this is a saddle-shaped surface. If the Gaussian curvature is 0, we have two cases. One is trivial, K1 equals K2 equals 0. This is a plane-shaped surface. The other one is 0 and other one is not 0. It's a cylindrical shaped surface. In one direction, there is no bending. In one direction, there is a bending. These are zero Gaussian curvatures. So we introduced main concepts to understand our theorem, to state our theorem. So let's state our theorem. Gauss's theorema egregium. The other name is the remarkable theorem of Gauss. Theorem states that Gaussian curvature is an isometric invariant. In other words, isometries preserves Gaussian curvature. So after stating the theorem, we will give three applications. One application is about Gaussian curvature, one application is about mean curvature, one application is about the theorem. So let's begin with the Gaussian curvature. Shape of the universe depends on its Gaussian curvature. If the Gaussian curvature of the universe is 0, it is flat. If it's negative, it is open and saddle shape. If it's positive, it is closed and spherical shape. So the universe is one of these three shapes. And the Gaussian curvature determines the shape of the universe. And shape of the universe determines two important things. One is ultimate fate of the universe. If the universe is flat or open, it is infinite and it is expanding. If the universe is closed, if the Gaussian curvature is positive, it is finite. The other thing is that distribution of galaxies. In one case, in the universe, galaxies are clustered. In one case, galaxies are more spread out to universe. So Gaussian curvature determines some important concepts about universe. So the second application is about mean curvature. What is a minimal surface? Minimal surface is a surface that minimizes the area within a boundary. I have a boundary that minimizes this area, the surface area. In mathematically, zero mean curvature surfaces are minimal surfaces. Think that K1 plus K2, and if it's zero, these are minimal surfaces. Where we use minimal surfaces, the production of efficient materials will depend on the properties of minimal surfaces. Because if you want to produce a lightweight material, optimal material, efficient material, you can know about, you should know about minimal surfaces. In technology, in production of technological materials, we use the properties of minimal surfaces. And the second thing is that some biological structures are minimal surfaces, such as biological membranes. These are minimal surfaces. In order to understand the biological membranes, we should know about minimal surfaces. And also, if you want to produce medical implants, again, we should use minimal surfaces properties. So it is useful to scientists and engineers. So the main application of this presentation is incorrect world maps. Everywhere in the world, everywhere in the universe, we don't have a flat, correct map because the theorem states Gaussian curvature of a world is positive. It is a spherical shape. But our papers are flat and Gaussian curvature is zero. So we cannot make a proper map, correct map, such that preserves lengths, surface areas, or angles. There are distortions. In general, we use projections. And the popular one is spherical projection. And spherical projection does not don't preserve the surface areas. You can see the Greenland here. In the top of the map, Greenland looks very big, but when we move down to side of the Africa, it looks like very small. So this is because the Gauss theorem egregium. The projections are not correct maps. They don't preserve surface areas or lengths or angles. So I think this is an impressive and interesting fact. Every map is wrong that we use. So if you're interested in this topic, you can look my references. And if there's any question, I can answer them. Thank you for listening.